In the profound and silent darkness of space, our solar system is a place of constant, immense motion. Planets trace their ancient, elliptical paths around the sun, and moons orbit their parent worlds with gravitational grace. But they are not alone. Countless smaller bodies, asteroids and comets, also drift through this void, remnants from the dawn of creation, following orbits that often intersect with our own. For most of human history, the sky was a canopy of serene, unchanging lights. But we now understand that it is also a shooting gallery, and our Earth has been a target many times before. It's a story that unfolds on a cosmic scale, and we'd love to know where you're joining us from on our own small planet. Let us know in the comments where and at what time you're listening, and be sure to subscribe to be notified of our future stories. About 66 million years ago, a colossal asteroid, estimated to be at least 10 kilometers, or about 6 miles wide, screamed through the atmosphere and struck the planet in what is now the Yucatan Peninsula. The impact unleashed an energy equivalent to billions of atomic bombs, triggering global firestorms, colossal tsunamis, and plunging the world into a long, dark winter that led to the extinction of the dinosaurs and 3/4 of all life on Earth. More recently, in the year 2013, a far smaller object, only about 20 meters or 66 feet in diameter, exploded in the skies over the Russian city of Chelyabinsk. It shattered windows for miles around and injured over 1,500 people. A stark reminder that the threat from the cosmos is not merely a relic of the distant past. For generations, we could do nothing but watch and wonder, passive observers in a universe that could at any moment deliver a catastrophic blow. But humanity is not a species content to be a passive observer. This is the story of the moment we decided to act. The story of the Double Asteroid Redirection Test, or DART. It is the story of humanity's first attempt to reach out into the vastness of space and intentionally alter the path of a celestial body, a mission not of destruction, but of a gentle, precise nudge. This was a test, a planetary defense drill conducted on a harmless asteroid system millions of miles away, to see if we could, if we ever needed to, protect our own world from a genuine threat. It is a narrative of human ingenuity, a testament to our ability to confront cosmic challenges with science and foresight, and the beginning of our journey to become not just inhabitants of our world, but its guardians. That journey to guardianship did not begin with the powerful launch of a sophisticated spacecraft, but with a quiet and persistent question that had intrigued astronomers for centuries. For a long time, there appeared to be a conspicuous gap in the cosmic architecture of our solar system, a vast, empty space between the orbits of Mars and Jupiter. An 18th century astronomical observation known as the Titius Bode Law suggested a planet should be there. But for years, none was found. It was a celestial mystery that captivated astronomers across Europe, who organized a collaborative effort, a group they called the Celestial Police, to hunt for this missing world. But the discovery would not be theirs. Instead, it fell to a Sicilian astronomer named Giuseppe Piazzi. On the very first night of the 19th century, January 1, 1801, while meticulously charting the stars from his observatory in Palermo, Piazzi noticed a tiny pinprick of light that was not on his maps. He watched it over the following nights, observing its slow but definite movement against the background of fixed stars. He had found something. Initially, he believed he had discovered a comet, but its slow, regular orbit suggested otherwise. He cautiously announced his finding, and the great mathematician Carl Friedrich Gauss developed a new method for calculating its orbit, confirming that it lay precisely in the gap between Mars and Jupiter. Piazzi named his discovery Ceres, after the Roman goddess of agriculture and the patron goddess of Sicily. For a brief time, the solar system had a new planet. The mystery, it seemed, was solved, but the solution was short-lived. Just a year later, another object, Pallas, was found in a similar orbit. Then came Juno in 1804, and Vesta in 1807. The orderly solar system of planets was suddenly becoming crowded. It was the brilliant astronomer William Herschel who proposed a new classification for these objects. Observing that they were so small, they appeared as mere points of light in telescopes. Unlike the distinct disks of planets, he suggested the name asteroid, from the Greek word meaning star-like. The name stuck, and the vast expanse between Mars and Jupiter became known as the asteroid belt, a sprawling junkyard of primordial material, leftovers from the formation of the solar system that never coalesced into a planet. For over a century, these asteroids remained objects of scientific curiosity, distant rocks of little consequence to life on Earth. That perception began to shift in 1898 with the discovery of an asteroid named Eros. Unlike its siblings in the main belt, Eros had a peculiar, elongated orbit that brought it swinging inside the path of Mars. It was the first known near-Earth asteroid, a member of a new class of objects whose cosmic journeys could, one day, intersect with our own. The first true, visceral hint of the destructive power these objects carried arrived a decade later. On the morning of June 30, 1908, a colossal explosion ripped through the sky over a remote, sparsely populated forest region near the Pod-Kamenaya Tunguska River in Siberia. The blast was immense, estimated to be hundreds of times more powerful than the atomic bomb that would later be dropped on Hiroshima. It flattened more than 2,000 square kilometers, nearly 800 square miles, of forest, felling some 80 million trees in a radial pattern. Their trunks all pointing away from the epicenter of the explosion. Yet, it left no crater. For years, the event was shrouded in mystery, with theories ranging from a volcanic eruption to an encounter with a tiny black hole. The most likely explanation, we now understand, was the air burst of a large meteoroid or comet fragment, an object perhaps 50 to 60 meters or 160 to 200 feet across, which disintegrated and vaporized several miles above the ground. The Tunguska event was a profound warning, a demonstration that the cosmos could unleash devastating energy upon the Earth with absolutely no notice. Still, the idea of doing anything about it remained firmly in the realm of science fiction. The tools to even contemplate such a feat simply did not exist. That changed dramatically in the mid-20th century, born from the geopolitical anxieties of the Cold War. The race to develop nuclear weapons and the rockets to deliver them had, as an unintended consequence, equipped humanity with two key technologies: immense, concentrated power and the ability to travel beyond Earth's atmosphere. For the first time, we had both a shield and a spear, and a few forward-thinking minds began to wonder if the technologies designed as instruments of war could be repurposed for planetary salvation. The first serious scientific exploration of this idea took place in the spring of 1967 at the Massachusetts Institute of Technology. A class of graduate engineering students was given a seemingly fantastical assignment by their professor, Paul Sandorf. The task was part of a series of hypothetical planetary engineering challenges. A real near-Earth asteroid named 1566 Icarus had been discovered in 1949. Its orbit was known to be eccentric, a long ellipse that carried it closer to the Sun than Mercury, and then flung it out past Mars. Calculations showed that in 1968, Icarus would make a close but perfectly safe pass of Earth. The students' assignment was to treat this pass as a hypothetical impact scenario. They were given a deadline. Icarus will strike the Earth in 600 days. Your mission is to stop it. This was Project Icarus. The students delved into the problem with serious engineering rigor. They calculated the asteroid's mass and trajectory, and the energy required to alter its course enough to miss the Earth. Their conclusion, published in a detailed report, was both terrifying and ingenious. They proposed using the most powerful rocket in existence at the time, the Saturn V, the very same rocket that would soon carry astronauts to the Moon. They envisioned a fleet of these rockets, each armed with a 100-megaton nuclear warhead, launched in waves to intercept the asteroid. Their plan was not to shatter Icarus into a cloud of smaller, but still dangerous fragments. Instead, they proposed a series of standoff explosions. By detonating the warheads at a calculated distance from the asteroid's surface, the intense burst of X-rays and gamma rays would flash heat a layer of rock into vapor. This vapor, blasting away from the surface would act like a powerful rocket thruster, imparting a gentle but persistent push to the asteroid. Repeated pushes from multiple explosions would, over time, nudge Icarus into a new, harmless orbit. Project Icarus was a theoretical exercise, but it marked a pivotal moment. It was the first time that asteroid deflection was treated not as fantasy, but as a solvable engineering problem. It laid the conceptual groundwork for the two main strategies that would dominate planetary defense thinking for decades: the kinetic impactor, essentially a cosmic cannonball, and the nuclear standoff, a more powerful but also more complex option. The final pieces of the puzzle, the ones that would elevate the asteroid threat from a niche academic concern to a serious matter of international policy, were put in place by pioneering scientists who taught us to read the scars on our own planet. Geologist Eugene Shoemaker, who had dreamed of being an Apollo astronaut but was grounded by a medical condition, dedicated his life to studying impact craters. He meticulously proved that craters like the Barringer crater in Arizona were not the result of volcanic activity, but were gouged out by high-velocity impacts from space. He and his wife, Carolyn, along with David Levy, would later discover the comet Shoemaker-Levy 9, and the world watched in awe in 1994 as it was torn apart by Jupiter's gravity and its fragments slammed into the gas giant's atmosphere, leaving dark, Earth-sized bruises that persisted for months. The event was a spectacular solar system scale demonstration of what happens when a planet takes a hit. Then, in 1980, the father and son team of Luis and Walter Alvarez, along with their colleagues, offered a stunning explanation for one of the greatest mysteries in the history of life: the extinction of the dinosaurs. They had discovered a thin, worldwide layer of clay, rich in the element iridium, an element rare on Earth's surface, but abundant in asteroids. They proposed that this layer was the fallout from a massive asteroid impact 66 million years ago. Their hypothesis, initially met with skepticism, was spectacularly confirmed with the discovery of the Chicxulub crater, a 150-kilometer or 93-mile wide impact structure buried beneath the Yucatan Peninsula, dating to precisely the right time. The case was closed. The threat was no longer theoretical or hypothetical. It was written into the very geology and fossil record of our planet. This growing mountain of evidence spurred action. In 1998, the United States Congress issued a directive to NASA, mandating that the agency detect and catalog 90% of all near-Earth asteroids 1 kilometer, about 0.62 miles, in diameter or larger. This was the size of object that could cause a global catastrophe. This mandate gave rise to a new generation of robotic telescopes, automated sky surveys like linear and pan-stars, which scanned the heavens night after night, taking millions of images and using sophisticated software to identify the faint, moving specks of light that were asteroids on a near-Earth trajectory. The era of passive observation was ending. The era of active searching had begun. We were beginning to map the celestial shooting gallery, identifying the potential threats. And with that knowledge came the inevitable, pressing question: if we found one with our name on it, what could we actually do? The theories from Project Icarus and decades of subsequent research needed a real-world test. Humanity needed to take its first tentative step from being a potential victim of cosmic chance to an active protector of its own destiny. We needed a target. We needed a plan. And we needed a messenger to carry our intentions into the void. And that messenger needed a destination. The ideal target for such an unprecedented experiment could not be just any asteroid plucked from the cosmic haystack. The criteria were incredibly specific and demanding. First and foremost, the target had to be safe. It was an absolute requirement that the mission could not, under any circumstances, accidentally push an asteroid onto a collision course with Earth. The celestial object chosen for this planetary defense drill had to pose no threat, either before the test or after. Secondly, the effect of the impact had to be measurable from a great distance. The change in the asteroid's trajectory would be minuscule, a cosmic nudge measured in fractions of a degree, and scientists on Earth, millions of miles away, needed a reliable way to confirm that their cosmic slingshot had actually worked. Finally, the target needed to be of a relevant size, a stand-in for the type of asteroid that poses the most likely threat, not the civilization-ending behemoths that are thankfully rare and relatively easy to track, but the smaller, city-killer-sized objects that are far more numerous and harder to detect. The search for this perfect celestial laboratory led scientists to a faint point of light first spotted in the year 1996. It was discovered by astronomer Joe Montani of the Spacewatch survey at the Kitt Peak National Observatory in Arizona, part of the new generation of automated sky searches mandated by the American Congress. Like all newly found asteroids, it was given a provisional designation, 1996 GT. For several years, it was just another entry in the growing catalog of near-Earth objects, one of thousands. But as astronomers continued to track its path and refine its orbit, they noticed something peculiar about the light it reflected. The asteroid's brightness seemed to fluctuate in a complex, repeating pattern, a rhythmic dimming and brightening that hinted at something more than a single tumbling rock. The first definitive clues to its true nature came not from light, but from radio waves. In 2003, using the powerful planetary radar systems at the Arecibo Observatory in Puerto Rico and the Goldstone Solar System radar in California's Mojave Desert, scientists bounced signals off the asteroid. This technique, a form of cosmic sonar, allows astronomers to build a rough picture of an object's size, shape, and rotation. The echoes that returned from 1996 GT were astonishing. they revealed not one object, but two, locked in a gravitational embrace. The larger object was the primary asteroid, but it had a tiny moonlet orbiting it. The light curve data, particularly the detailed observations from a team led by Czech astronomer Peter Prévec, confirmed the finding. The regular dips in brightness were caused by the two objects eclipsing each other from our point of view on Earth, as the tiny moon passed in front of and then behind its larger companion. 1996 GT was a binary asteroid, a system of two worlds dancing together through the void. This discovery made it an object of intense scientific interest. In honor of its dual nature, its discoverer, Joe Montani, gave it the official name Didymos, the Greek word for twin. For many years, Didymos and its moonlet, which remained unnamed, were studied for what they could teach us about the formation and evolution of these small, rocky bodies. They were a perfect natural laboratory. And then, as the concepts of planetary defense matured from theory into a concrete mission plan, a team of scientists realized that Didymos was more than just a scientific curiosity. It was the perfect target. It perfectly met all the criteria. The Didymos system's orbit brought it near Earth, but did not cross our path, making it completely safe. The 2022 close approach would place it at a distance of about 11 million kilometers, or just under 7 million miles, which was ideal for observation by a worldwide network of ground-based telescopes. Its binary nature offered the perfect solution to the problem of measurement. Trying to detect the infinitesimally small change in the trajectory of a single asteroid traveling around the Sun would be like trying to measure if a speeding bullet has moved a hair's breadth to the side from miles away. It would be a monumental challenge, potentially taking years of observation to confirm. But measuring the change in the orbit of the moonlet around Didymos was a far simpler and more elegant problem. The moonlet, later to be named, completed one full orbit of its parent in a precise and predictable period, 11 hours and 55 minutes. This orbital period was the mission's master clock. The DART spacecraft would not target the main asteroid, Didymos, but its smaller companion. The impact, scientists calculated, should shorten the moonlet's orbital period by several minutes. This was a change large enough and rapid enough that it could be easily and unambiguously timed by telescopes on Earth, simply by watching for the eclipses. They could measure the before time and the after time. The success of the mission would not be a matter of subtle astrometry, but of simple, definitive timekeeping. And so, the target was chosen. The larger asteroid, Didymos, is a spinning, top-shaped body, about 780 meters, or 2,560 feet, in diameter, roughly the size of a small mountain. It rotates rapidly, completing a full turn every 2.26 hours. Its shape, with a pronounced bulge around its equator, is characteristic of what astronomers call a rubble pile asteroid. It is not a solid, monolithic piece of rock, but rather a loose agglomeration of boulders, gravel, and sand, all held together by the gentle tug of their own mutual gravity. It is less a single object and more a self-gravitating heap of cosmic debris. Orbiting this spinning mountain is the mission's true target, the moonlet. For a long time, it was referred to simply as Didymoon. But an undertaking of this historic importance required a more fitting name. Planetary scientist Cleomenes Tsiganis from the Aristotle University of Thessaloniki proposed the name Dimorphos. It is a Greek word meaning having two forms. The name was a beautifully poetic and scientifically precise choice, because Dimorphos would indeed have two forms. Its original form, as it existed in space before the test, and its second form, after humanity had touched it, with a slightly altered orbit and a new crater marring its surface. Dimorphos is a tiny world, just 160 meters, or about 530 feet, across, roughly the size of the Great Pyramid of Giza. It is also believed to be a rubble pile, a loose collection of rocks held together by gravity. It circles Didymos at a distance of just over 1 kilometer, or about 3/4 of a mile, completing its stately, rhythmic dance every 11 hours and 55 minutes. This tiny, distant moonlet, orbiting its parent millions of miles from Earth, was the perfect stand-in for the type of asteroid that poses a genuine threat. An object the size of Dimorphos, were it to strike a populated area, would not cause a global catastrophe, but it would release energy equivalent to many nuclear bombs, enough to completely obliterate a major city and cause regional devastation on a continental scale. The Didymos binary system, a chance discovery born from a systematic search, had become the designated stage for humanity's first dress rehearsal for planetary defense. The characters were in place: the spinning, mountain-sized primary actor, Didymos, and its small, targeted understudy, Dimorphos. The plot was written: a high-speed kinetic impact to alter an orbit. The audience was ready, with telescopes across the globe prepared to watch the performance. All that was missing was the protagonist, the messenger that would travel across the vastness of space to deliver its single, crucial, history-making blow. That messenger, the protagonist of this cosmic drama, was a machine of elegant and focused purpose, an emissary designed not for discovery in the traditional sense, but for a single, history-making act of kinetic intervention. Its name was DART, the Double Asteroid Redirection Test. The task of building this cosmic emissary fell to the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland, a place with a long and storied history of reaching for the outer limits. For decades, the Applied Physics Laboratory, or APL, had been the birthplace of robotic explorers that ventured to the frontiers of the solar system. It was here that the New Horizons spacecraft was built, the probe that would journey for nearly a decade to give humanity its first close-up look at the distant, icy world of Pluto. And it was here that the Parker Solar Probe was forged, a daring mission to fly into the very atmosphere of the sun, to touch a star. But DART was different. It was not designed to orbit, to land, or to spend years collecting scientific data. It had one job, and one job only: to fly for 10 months through the cold vacuum of space and then cease to exist in a precisely targeted high-speed collision. It was, in essence, a cosmic cannonball, but one imbued with an extraordinary intelligence. DART was a relatively small spacecraft. Its main body was a boxy structure, roughly the size of a large vending machine, measuring about 1.2 by 1.3 by 1.3 meters, or about 4 by 4.3 by 4.3 feet. At the time of its launch, it weighed a total of 610 kilograms, or roughly 1,345 pounds. Most of that mass was its fuel, and the spacecraft body itself, a dense package of energy and electronics designed to be delivered with pinpoint accuracy. To power its journey, DART relied on the sun, but with a novel and elegant technology. Instead of traditional rigid solar panels that folded out like an accordion, DART was equipped with a new system called the Roll-Out Solar Arrays, or ROSA. At launch, these arrays were stored as two tightly wound cylinders, like scrolls of high-tech parchment. Once in the vacuum of space, they unfurled into two long, flexible wings of advanced solar cells. When fully deployed, they stretched to a total length of 18.6 meters, or about 61 feet, from tip to tip, giving the small spacecraft an impressive and graceful wingspan. This innovative design was not only lighter and more compact than its rigid predecessors, but it was also a critical technology demonstration, proving out a new way to power future missions into deep space. Those arrays fed electricity to another piece of advanced technology at the heart of the spacecraft: its engine. DART was propelled by the NASA evolutionary Xenon Thruster Commercial, or NEXT-C. This was not a conventional chemical rocket engine that creates thrust through a violent, fiery explosion. Instead, it was an ion thruster, a marvel of efficiency that generates a gentle but incredibly persistent push. The engine used electricity from the solar arrays to ionize atoms of xenon, a heavy, inert gas, giving them a positive electric charge. Powerful magnets then accelerated these charged ions and shot them out of the engine at tremendous speeds, over 145,000 kilometers per hour, or about 90,000 miles per hour. The thrust produced at any given moment was incredibly slight, about the same as the pressure exerted by a single piece of paper resting on the palm of your hand. But in the frictionless environment of space, this faint but constant push, maintained over months, allowed DART to build up immense velocity and fine-tune its trajectory with a level of precision chemical rockets could never match. But the true genius of the DART spacecraft resided not in its body or its engines. but in its mind and its vision. It had only one instrument, a single piece of hardware that served as its eyes, its brain, and its sole purpose for existing. It was called the Didymos Reconnaissance and Asteroid Camera for Optical Navigation, or DRACO. This instrument was a high-resolution camera, a powerful telescopic lens derived from the LORRI instrument on the New Horizons Pluto mission, a lineage that gave it an impeccable pedigree for imaging distant, dim objects. For most of the 10-month journey, DRACO was a passive passenger, sleeping while the spacecraft followed its pre-programmed path. But in the final critical hours of the mission, it would awaken to become the star of the show. It was DRACO's job to see the target. From millions of miles away, the Didymos system would appear as a single, unresolved point of light. As DART raced closer at a speed of nearly 6.6 kilometers per second, or about 14,000 miles per hour, DRACO would begin to distinguish the two asteroids. It would see the larger Didymos and the tiny, faint, moonlit Dimorphos orbiting it. These images fed directly into the spacecraft's brain, a sophisticated guidance system called Small Body Maneuvering Autonomous Real-Time Navigation, or SMART-NAV. This was the key to the entire mission, because in those final hours, direct human control was impossible. At its impact distance of 11 million kilometers, the speed of light imposed a communications delay of about 38 seconds each way. A command sent from Earth would take 38 seconds to reach the spacecraft, and the result of that command would take another 38 seconds to travel back. A round-trip time of over a minute meant that a human operator with a joystick would be like a driver trying to navigate a high-speed chicane while looking in a rear-view mirror that showed the past. It was an impossible task. The spacecraft had to make its own decisions. For the last 4 hours of its life, DART was completely autonomous. The SMART-NAV algorithms took the images from DRACO, identified the Didymos system, and began firing the spacecraft's thrusters to refine its course. In the final hour, with Dimorphos now clearly visible as a separate object, the navigation system locked on. Its sole command was to ignore the larger, brighter Didymos and steer the entire spacecraft directly into the center of the tiny moonlet. Every correction, every puff from the thrusters was calculated and executed by the onboard computer in real time, a brilliant and lethal demonstration of artificial intelligence. DART was not traveling alone on its historic journey. Tucked away on its side, waiting for its own moment to shine, was a tiny companion. It was a CubeSat, a miniature satellite about the size of a briefcase, built by the Italian space agency, the Agenzia Spaziale Italiana. Its name was Lycia Cube, short for Light Italian. Cube sat for imaging of asteroids. Weighing just 14 kilograms, or about 31 pounds, Lycia Cube was the mission's dedicated photojournalist. Its job was to bear witness. 15 days before the final impact, DART released its tiny companion, pushing it away with a gentle spring. Lycia Cube then used its own small propulsion system to adjust its course, flying on a path that would take it past the Didymos system about 3 minutes after DART's collision. It was equipped with 2 cameras, Leia and Luke, which were tasked with capturing images of the moment of impact itself. The resulting cloud of rock and dust, known as the ejecta plume, and the newly formed crater on Dimorphos's surface. It would also photograph the opposite hemisphere of the asteroid, the side that DART itself would never see. Lycia Cube was the designated observer, the crucial third party that would provide the visual evidence of what transpired in that remote, silent corner of the solar system. Together, this international pair, the American impactor and the Italian observer, were assembled and meticulously tested in the pristine clean rooms at APL. Engineers in white gowns and face masks moved around the spacecraft, checking every circuit, testing every thruster, and polishing the lens of its single, vital eye. By the late summer of 2021, the messenger was complete. It was no longer a collection of plans, circuits, and exotic metals. It was a machine with a destiny, a sleek and intelligent projectile poised to embark on a journey that would culminate in a silent, brilliant flash, a cosmic exclamation point marking a new chapter in humanity's relationship with the heavens. The journey from a clean room in Maryland to a collision course millions of miles away began on a cool, clear night on the coast of Central California. The launch site was Vandenberg Space Force Base, a place where the rugged, chaparral-covered hills of the Pacific coast meet the cutting edge of aerospace technology. It is a landscape of dramatic contrasts where wild deer and mountain lions roam within sight of towering launch gantries and sprawling radar installations. It was from this place, on the 24th of November in the year 2021, that DART was scheduled to leave the Earth forever. The vehicle chosen to hurl the spacecraft into the cosmos was a testament to the new era of spaceflight, a SpaceX Falcon 9 rocket. This was not a disposable, single-use machine like the giant Saturn V's of the Apollo era, but a sleek, reusable launch vehicle that had revolutionized access to space. Its first stage, the powerful booster that would provide the initial muscle to tear away from Earth's gravity, had flown twice before, a veteran of 2 previous satellite launches. Now, standing tall on Space Launch Complex 4, it was prepared for its third and final flight, its white fuselage gleaming under the powerful floodlights, venting clouds of super-chilled liquid oxygen vapor that swirled around its base like a mythical fog. The rocket was a 2-stage vehicle, standing nearly 70 meters, or 230 feet, tall. Encased in its payload fairing at the very top, like a precious jewel in a protective casket, sat the DART spacecraft and its tiny Italian companion, Lycia Cube. For the engineers and scientists at the Applied Physics Laboratory, and for the entire planetary defense community, This was a moment of profound anticipation, the culmination of years of design, construction, and tireless planning. In the final hour before the scheduled 10:21 in the morning Pacific Standard Time launch, the countdown entered its automated sequence. Control was handed over from human operators to the onboard computers of the Falcon 9. A meticulously choreographed symphony of valves opening, pumps spinning, and systems checks began. The rocket was loaded with its highly refined kerosene fuel and liquid oxygen, a cryogenic propellant chilled to a frigid -183 degrees Celsius, or -297 degrees Fahrenheit. In the control rooms at Vandenberg and at SpaceX headquarters in Hawthorne, California, a quiet, focused tension settled over the teams. Every screen was a sea of green, indicating all systems were nominal. All conditions go for launch. The final minutes ticked away with the calm, measured cadence of the launch director's voice calling out the milestones. 10, 9, 8, 7. The engine ignition sequence began. A torrent of water, a sound suppression system designed to protect the rocket from the acoustic energy of its own engines, flooded the launch pad. 6, 5, 4. The 9 Merlin engines on the first stage booster flared to life. 3, 2, 1. The hold-down clamps released. 0. With a deafening roar that rolled across the hills and out over the dark waters of the Pacific Ocean, the Falcon 9 lifted off. For a heart-stopping moment, it seemed to hang in the air, a brilliant, incandescent pillar of fire that turned night into day. Then, with gathering speed, it ascended, pushing against the immense weight of Earth's gravity. The sound, a deep, crackling thunder, washed over observers miles away, a physical force that vibrated in their chests. The rocket climbed, a searing point of light against the star-dusted blackness of the California sky. Inside the fairing, DART was experiencing the violent shudder and crushing acceleration of its birth into the cosmos. 70 seconds into the flight, the rocket reached the point of maximum aerodynamic pressure, the moment of greatest stress on its structure as it blasted through the densest part of the atmosphere. It powered through seamlessly. At 2 minutes and 30 seconds after liftoff, the 9 first stage engines shut down. The booster separated, its job done, and began its own remarkable journey back to Earth. As the second stage engine ignited to continue pushing DART into orbit, the first stage performed a series of elegant, automated maneuvers. It fired its cold gas thrusters to flip itself around, deployed grid fins to steer itself through the atmosphere, and performed a final re-entry burn to slow its descent. It flawlessly landed on a robotic drone ship named Of Course I Still Love You, stationed hundreds of miles out in the Pacific, a fiery, precise touchdown that had become almost routine, yet remained one of the most breathtaking sights in modern engineering. Meanwhile, the second stage continued its burn, carrying DART higher and faster. A few moments after the first stage separated, the protective payload fairing, no longer needed in the vacuum of space, split open like a clamshell and fell away. For the first time, DART was exposed directly to the harsh environment of space. The second stage engine fired for several minutes, placing DART into a temporary parking orbit around the Earth. Then, for nearly an hour, they coasted in silence, a quiet, looping ballet that positioned them perfectly for the final escape. Over the Indian Ocean, shielded from the sun by the body of the Earth, the second stage engine reignited. This was the final, critical burn, the trans-lunar injection that would provide the precise amount of velocity needed to break free from Earth's gravitational embrace and begin its long, coasting journey into the solar system. The engine fired for several more minutes, accelerating the spacecraft to its escape velocity of over 11 kilometers per second, or nearly 7 miles per second. 55 minutes after leaving Vandenberg, the engine shut down for the last time. A few minutes later, a series of gentle pushes from a pneumatic system released the DART spacecraft from its launch adapter. It drifted away from the now inert rocket stage, a solitary traveler, finally on its own. The first moments of a spacecraft's independent life are always the most tense. Back at the Mission Operations Center at the Applied Physics Laboratory, the team waited for the first signal. The spacecraft needed to autonomously power up, stabilize its orientation, and turn its antenna toward Earth to say hello. The minutes stretched into an eternity. Then it came. A stream of telemetry data appeared on the screens, a faint whisper of a signal from thousands of miles away, confirming that DART was alive, healthy, and on its way. The control room, a place of stoic professionalism, erupted in a wave of applause and relieved celebration. The next critical milestone came just 2 hours after launch. On command from the ground, the spacecraft began the delicate process of unfurling its ROSA solar arrays. The 2 tightly wound cylinders of solar cells slowly unspooled, stretching out into their full, magnificent 61-foot wingspan. As they locked into place and turned to face the distant sun, telemetry confirmed that they were generating power, charging the spacecraft's batteries and providing the lifeblood for the long journey ahead. DART was now fully deployed, a lone, winged messenger of humanity, gliding silently away from its home world. Ahead lay a 10-month voyage of nearly 700 million miles, a looping, elliptical path around the sun that would slowly, inexorably, bring it to its rendezvous with the Didymos system. The launch was over, a flawless and powerful beginning. Now, the long, quiet vigil began, a period of patient cruising, punctuated by occasional course corrections and system checks, as DART sailed through the immense, dark ocean of interplanetary space, its single eye fixed on a distant, fateful appointment. That distant, fateful appointment was set for the 26th of September in the year 2022. The 10-month journey that preceded it was far from a passive drift. It was a period of meticulous preparation, a long and patient dress rehearsal for the final, frantic moments. Throughout its voyage, DART's human pilots at the Applied Physics Laboratory kept a watchful eye, periodically waking the spacecraft's systems to check their health. They fired its powerful Next-C ion engine, not for a continuous push, but in a series of planned maneuvers to subtly refine its trajectory, nudging it onto the perfect intercept course. They calibrated its single, all-important eye, the Draco camera, pointing it at bright, well-known stars like Vega and Jupiter to ensure its vision was sharp and its pointing precise. For most of this journey, the target, the Didymos system, was completely invisible, lost in the glare of the sun and indistinguishable from the countless other faint specks of light in the cosmos. But as the summer of 2022 drew to a close, and DART closed the final millions of miles to its destination, the target began to emerge from the blackness. At first, in late July, it was just a single, pixelated point of light in Draco's images, a faint ghost barely visible against the noise of deep space. But it was there. The hunt was on. The spacecraft was now close enough to see its quarry. And with every passing day, the faint point of light grew steadily brighter. This was the beginning of the end game. By early September, the Draco camera was imaging the Didymos system daily, its pictures helping navigators on Earth to make the final minute course corrections. The spacecraft was performing flawlessly, a testament to the years of engineering and testing. It was on a trajectory so precise that it was aimed at a patch of space less than 15 kilometers, or about 9 miles, wide, centered on the asteroid. All that remained was the final terminal phase, the most daring and uncertain part of the entire mission. This was the moment where humanity had to let go. On the 26th of September, with the Didymos system now 11 million kilometers, or just under 7 million miles away, the mission reached its point of no return. The mission controllers at APL gathered around their consoles for the final act. They sent their last set of commands to the spacecraft, a final bundle of instructions that essentially told the machine, "You're on your own now." At this distance, the time delay for a radio signal to travel from Earth to DART and back was over a minute. Piloting the spacecraft in real time was a physical impossibility. The final, crucial decisions had to be made by the spacecraft itself. 4 hours before the predicted impact, a switch was flipped. The human pilots, separated by an unbridgeable gulf of time and space, handed the reins to their robotic proxy. DART's brain, The small body maneuvering autonomous real-time navigation system, or SMART nav, took command. The spacecraft was now a fully autonomous, sentient projectile. Its programming was elegant and brutally simple. Find Dimorphos and hit it. For the first 3 hours of its autonomous flight, Smart Nav focused on the brighter of the two objects, the main asteroid Didymos. It used this as its guiding beacon, firing DART's thrusters in tiny, precise puffs to keep the spacecraft perfectly centered on its target. All the while, the Draco camera was taking pictures, its digital eye staring intently at the approaching asteroid system. The images, once every second, streamed back to Earth, a silent, visual countdown that allowed the mission team to watch over the shoulder of their robotic pioneer, spectators to a drama they had set in motion but could no longer control. About 1 hour before impact, the mission reached its most critical moment of decision. DART was now close enough that Dimorphos, the tiny moonlet, began to separate from the glaring light of its larger parent. It emerged as a distinct, separate point of light, a tiny companion in a gravitational dance. SMART. Nav's algorithms, which had been programmed for this very moment, saw it. The system executed its core command. It shifted its attention, its digital gaze, from Didymos to the smaller, fainter Dimorphos. It was now locked on. For the final hour, DART was no longer just flying toward an asteroid system. It was flying toward a specific 160-meter or 530-foot wide world. The final 60 minutes were a cascade of increasing speed and escalating precision. As DART hurtled forward at a relentless 6.6 kilometers per second, or nearly 14,000 miles per hour, Dimorphos grew from a single pixel to 2, then to 4, and then into a resolved, albeit fuzzy, blob. Smart Nav was in complete control, its software processing the incoming images in real time, constantly calculating the spacecraft's position relative to the center of Dimorphos. Any tiny deviation from a perfect collision course was instantly corrected with a burst from one of the 12 hydrazine thrusters. It was an act of celestial marksmanship on an unimaginable scale, akin to firing a rifle from one city to hit a specific coin in another. While both the rifle and the coin are moving at orbital velocities. The images streaming back to Earth became more and more astonishing with each passing minute. Dimorphos began to take shape, its form revealing itself to human eyes for the very first time. It was not a smooth, round sphere, but an elongated, egg-shaped body, a jumble of rock and dust. Its surface, once a mystery, resolved into a landscape of boulders, craters, and regolith. In the final seconds, the images were breathtaking. DART was now so close that its camera could no longer see the entire asteroid. Its field of view was filled with a stark, alien terrain of gray rocks and deep black shadows. It was a world that no human had ever seen, and DART was its first and last visitor. The pictures, arriving on Earth with their 38-second delay, showed a field of boulders growing larger and larger, rushing up to meet the camera. In the mission control room, the team watched in rapt, silent awe. They saw a large boulder, then another. The texture of the rock was visible. The image refreshed, showing the surface in even greater, more granular detail. Then, the next image that was due to arrive never came. The screen froze on a final, incomplete picture, a sliver of the asteroid's surface. The stream of data from DART, the steady heartbeat of its telemetry, flatlined. A profound and sudden silence replaced it. The spacecraft, after its 10-month journey and its final, brilliant, autonomous flight, had ceased to exist. On a tiny, distant world, at 7:14 in the evening, Eastern Daylight Time, humanity had made its mark. The signal was gone, but back on Earth, the silence in the control room was broken by a spontaneous, overwhelming wave of cheers, applause, and tearful embraces. The impact was a success. DART's own story had ended in a silent, brilliant flash, but the larger story was just beginning. 3 minutes behind the point of impact, its tiny Italian companion, Lycia Cube, was now approaching the scene. Its own cameras ready to witness the immediate aftermath and capture the first images of the cloud of debris kicked up by this historic, human-made collision. The final, fragmented image from DART was a snapshot of its own demise, a silent testament to a mission accomplished. But in the cold, airless void, 11 million kilometers from Earth, the story continued without a sound. The collision itself was an event of immense, concentrated violence over in an instant. The 610 kilogram, or 1,345 pound spacecraft, traveling at a velocity that could cross a major city in the blink of an eye, slammed into the rocky surface of Dimorphos. In that moment, DART ceased to be a spacecraft. Its carefully constructed form, its solar arrays, its intelligent navigation system, all vaporized upon impact. The kinetic energy it carried, equivalent to the explosion of about 3 tons of TNT, was transferred directly into the asteroid. A shock wave, more powerful than any terrestrial earthquake, propagated through the tiny world, a shudder that passed through its loosely bound rubble. Pile structure in a fraction of a second. The impact site flashed with incandescent heat, instantly melting and vaporizing rock, gouging a new, human-made crater into the primordial surface of a world that had remained untouched for billions of years. But the most spectacular and scientifically crucial consequence was not the crater itself, but what came out of it. The impact blasted a colossal cone of rock, dust, and vapor away from the surface. In the vacuum of space, with no atmosphere to slow it down, this material, known as ejecta, expanded outwards in a brilliant, silent flower of debris. and flying towards this scene of cosmic creation was the mission's star witness, the tiny Italian briefcase-sized satellite, Lacia Cube. It had been released 15 days prior for this very moment. Its trajectory was carefully planned to miss the asteroid, but to fly by at a safe distance of about 55 kilometers, or 34 miles, just 3 minutes after DART's scheduled impact. This was the ringside seat. As Lacia Cube made its approach, its 2 cameras, Leah and Luke, began their work. They captured a sequence of images that were nothing short of breathtaking. The first pictures showed the Didymos system as DART had seen it. A larger body with a smaller companion. But then a new feature appeared. A brilliant fan of light erupted from the surface of Dimorphos. It was the ejecta plume, caught in the moments after its creation, shining brightly as it caught the light of the distant sun. Lacia Cube's images were a revelation. They showed a complex, structured plume with streamers and filaments of dust and rock expanding away from the impact site at high velocity. The brightness of this cloud was astonishing, far more luminous than the asteroid itself. For several minutes, Lacia Cube documented the immediate aftermath, its cameras capturing the plume as it grew and evolved. A ghostly, expanding nebula of debris. Having fulfilled its primary mission, the tiny CubeSat continued on its own path, its precious cargo of images stored safely in its memory, which it would slowly transmit back to Earth over the following weeks. But Lacia Cube was not the only observer. A vast and powerful network of eyes, the most sophisticated astronomical instruments ever built by humankind, were also turned towards that single, unassuming point of light in the constellation of Hydra. On the ground, dozens of telescopes across every continent, from the deserts of Chile to the mountaintops of Hawaii, were participating in a coordinated observation campaign. And in space, the 2 most powerful telescopes ever launched, the Hubble Space Telescope and the newly commissioned James Webb Space Telescope, pivoted their giant mirrors to stare at the event. What they all saw in the minutes following the impact was a dramatic and unambiguous change. The faint point of light that was the Didymos system suddenly brightened. It grew 3 times more luminous than it had been before the collision. This was not a flash of light from an explosion. In the vacuum of space, an impact creates no fiery blast. This brightening was the signature of the ejecta cloud. The vast, expanding plume of dust and rock was acting like a giant, temporary mirror, reflecting sunlight and making the entire system appear much brighter to distant observers. This was the first immediate confirmation from Earth that DART had not only hit its target, but had hit it hard, kicking up a tremendous amount of material. Over the next hours and days, the observations became even more spectacular. The cloud of ejecta, pushed by the gentle but constant pressure of sunlight, a phenomenon known as solar radiation pressure, began to stretch and distort. It formed a long, ghostly tail streaming away from Dimorphos, pointing away from the sun, just like the tail of a comet. This temporary, human-made comet grew to an astonishing length, stretching out for more than 10,000 kilometers, or over 6,000 miles, into space. Hubble and Webb captured stunning images of this evolving structure, a long, ethereal streamer of debris that remained visible for weeks. The sheer scale and brilliance of this ejecta plume was a surprise to many scientists. It told them something profound about the nature of their target. The vast quantity of material blasted into space suggested that Dimorphos was not a solid, competent rock, but a loosely bound rubble pile, its surface material easily displaced. This was a crucial piece of information for planetary defense. But more importantly, the enormous plume was the visible evidence of a key physical principle that the mission was designed to test: momentum enhancement. DART had delivered a push to the asteroid with its own kinetic energy, the simple physics of one object hitting another. But the rock and dust flying away from the impact site in the opposite direction provided an additional push, a recoil effect, much like the kick from a firing rifle. The departing ejecta acted like a powerful, temporary rocket engine, giving the asteroid a much greater shove than the spacecraft's impact alone could have provided. The visual evidence was overwhelming. The collision had been far more effective at moving the asteroid than even the most optimistic predictions had suggested. The impact itself was the climax of DART's own story. But for the scientific community, it was the opening scene. The key question, the ultimate measure of success, still remained to be answered. They had seen the bright flash and the spectacular plume of debris. They had witnessed the creation of a new, temporary comet in the solar system. But had they actually moved it? Had the orbital dance of Dimorphos around its parent, Didymos, a rhythm that had remained steady for eons, actually been changed? Answering that question would require not just spectacular images, but meticulous, patient, and precise timekeeping from the telescopes back on Earth. The real proof would be found in the ticking of a celestial clock. The celestial clock was the only thing that mattered. While the spectacular images of the impact and its ghostly, expanding tail of debris captured the world's imagination, for the scientists on the DART mission, they were merely the beautiful prelude to the real work. The mission's entire definition of success rested not on a picture, but on a number: the new orbital period of Dimorphos. To find that number, they had to listen for the ticking of that clock, a rhythm set by gravity and distance. And to do that, they needed to stare, patiently and persistently, at the faint light of the Didymos system. The method was beautifully simple in concept, but incredibly demanding in practice. It relied on a phenomenon known as a mutual event. From our vantage point on Earth, as Dimorphos circles Didymos, it regularly passes in front of its larger parent, causing a small, temporary dip in the total brightness of the system, a mini eclipse. Then, as it passes behind Didymos, another, similar dip in brightness occurs. The time between these successive dips is the precise measure of the moonlet's orbital period. Before the impact, an international consortium of astronomers had spent years meticulously measuring this rhythm. They had timed the eclipses again and again, establishing an incredibly precise baseline. They knew with certainty that Dimorphos completed one full orbit around Didymos every 11 hours and 55 minutes. This was the master number, the before snapshot, against which any change would be measured. Now, in the aftermath of the collision, the observation campaign began anew, but with a new challenge. The very ejecta cloud that had been so spectacular to witness was now a source of interference. It shrouded the binary system in a veil of bright, reflective dust, making it much harder for telescopes to distinguish the subtle dips in light from the two individual asteroids. It was like trying to hear a quiet, ticking clock in the middle of a noisy room. But the team was prepared. They used powerful telescopes equipped with sophisticated digital cameras and analytical software. In Chile's Atacama Desert, the Southern Astrophysical Research Telescope, or SOAR, and the telescopes at the Las Campanas Observatory stared at the system. In South Africa, the telescopes of the South African Astronomical Observatory joined the effort. Each night, as the Earth turned and brought the Didymos system into view, another observatory would pick up the watch. They collected what astronomers call light curves, graphs that plot the brightness of an object over time. In the days following the impact, these light curves were messy, contaminated by the glare of the ejecta. But as the dust cloud began to dissipate and stretch out into its long tail, the signal started to become clearer. The team could see the dips in brightness again. They were there. The clock was still ticking. But was it ticking at the same rate? The first few measurements were tantalizing, but not yet conclusive. They showed a definite change, but more data was needed to be certain, to refine the number and remove any margin of error. Night after night, the data poured in, with different teams around the world cross-checking each other's results. Finally, 2 weeks after the impact, the team had collected enough pristine data. They had timed enough eclipses. The noise from the ejecta had been accounted for. The answer was clear, unambiguous, and far more spectacular than they had dared to hope. The new orbital period of Dimorphos was 11 hours and 23 minutes. The impact of the DART spacecraft had shortened the moonlet's orbit by a full 32 minutes. The celestial clock had not just been nudged, it had been dramatically reset. To put this achievement in perspective, the DART mission's own definition of minimum success was a change of just 73 seconds. The result they had achieved was more than 25 times greater than that benchmark. It was an overwhelming, unequivocal success. This resounding victory immediately raised a new, fascinating question. Why had it worked so well? The answer lay in that brilliant cloud of ejecta. The DART spacecraft itself had delivered a simple kinetic push, a transfer of its own momentum to the asteroid. But the recoil from the tons of rock and dust blasted into space in the opposite direction had acted as a powerful, natural thruster. This recoil, this momentum enhancement, had provided a push that was many times more powerful than that of the spacecraft alone. By analyzing the change in the orbit, scientists could work backwards to calculate the total momentum transferred to the asteroid. Their calculations revealed that DART had imparted roughly 3.6 times more momentum than if the spacecraft had simply been absorbed by the asteroid without creating any ejecta. This was a critical discovery. It proved that the kinetic impactor technique is a viable and, in the case of a rubble pile asteroid, a highly efficient method for asteroid deflection. It meant that a future mission to deflect a genuinely threatening asteroid might not need a massive, heavy impactor. A smaller, well-targeted probe could be dramatically amplified by the asteroid's own material. The echoes of the impact continued to reveal new secrets. The data from Lycia Cube, once transmitted back to Earth, provided the first close-up portraits of Dimorphos. The images showed it to be an oblate spheroid, essentially a squashed egg-shaped body, confirming its classification as a rubble pile. Its surface was a chaotic jumble of boulders, with some as large as several meters, or more than a dozen feet, across. And the Hubble and James Webb Space Telescopes continued to monitor the evolving debris tail, discovering a second, fainter tail emerging a few days after the first. This twin tail was a complex and beautiful phenomenon, the result of different-sized dust particles being pushed around by the sun's radiation pressure at different rates. The mission had not just succeeded in its primary goal, it had provided a treasure trove of data on the physics of impacts and the nature of these small, mysterious worlds. The global nature of the effort was a testament to the power of scientific collaboration. It was an American spacecraft launched on an American rocket, carrying an Italian satellite, which was then observed by a worldwide network of telescopes, all focused on a single shared goal. It was a demonstration of what humanity can achieve when it works together to confront a cosmic challenge. The question had been asked, and the answer had been delivered with the force of a cosmic collision. Humanity, for the first time, had intentionally and successfully altered the motion of a celestial body. We now knew, not in theory or in simulation, but through direct, empirical evidence, that we had the ability to protect our planet. A new tool had been forged and tested, a fundamental capability that forever changed our relationship with the cosmos around us. The story of the double asteroid redirection test is, in the end, a story about a single, fundamental transition. It is the story of the moment humanity ceased to be merely a passive inhabitant of a cosmic neighborhood and took its first deliberate step toward becoming its active caretaker. For millennia, we looked to the heavens with a mixture of wonder and trepidation, aware of the immense, impersonal forces that governed the universe. We chronicled the passage of comets and the fall of meteorites, but the idea that we could influence these celestial events belonged solely to the realm of myth and later science fiction. The DART mission transformed that fiction into fact. It began with the quiet dedication of astronomers charting the skies, who found a perfect, harmless target in the Didymos system, a binary asteroid dancing 11 million kilometers, or nearly 7 million miles, from Earth. It was brought to life by the ingenuity of engineers who forged a sophisticated, autonomous messenger, a spacecraft designed not to explore, but to perform a single, decisive act. For 10 long months, this emissary journeyed through the void, a silent testament to human foresight. In its final, breathtaking hours, it navigated on its own, its electronic brain and single, unwavering eye making the critical decisions that led it to its target. The tiny moonlit Dimorphos, a world just 160 meters or 530 feet in diameter. The collision was a silent, brilliant success, a precise transfer of energy that was witnessed by a global chorus of telescopes on the ground and in space. The resulting 32-minute change in the asteroid's orbit was an unambiguous, resounding confirmation that the technique worked, and worked better than anyone had expected. DART was a test, a drill, a demonstration. But it was also a promise. It was a message sent not to the cosmos, but to ourselves. A declaration that we are not bound to suffer the same fate as the dinosaurs, that the same intelligence which allows us to comprehend the threats from the universe can also be harnessed to defend against them. We have now touched a celestial body with purpose and intent, not for conquest or discovery, but for protection. The silent, ever-present threat from the sky remains, but it is no longer a source of helpless fear. It is now a challenge we know we can meet, a cosmic conversation in which we have finally and decisively spoken back.